Okay, next speaker is Dr. Taejin Kim. Dr. Kim is currently working at Changminwoo Structural Consultant in Korea as a partner and head of research and technology division. He is a licensed professional engineer in the area of building structures and holds a PhD in civil engineering from UC Berkeley, USA. His research interests are in the field of earthquake engineering and steel structures. Please welcome Dr. Kim.
Thank you, Chairman, for interesting me. And good afternoon, ladies and gentlemen. I'm going to talk about actually intermediate result from our research project on tall buildings. This project is funded by Ministry of Land, Transportation, Maritime Affairs of our government. And this is an overview for today's presentation. So I'm going to talk about first structural design issues and preliminary design and modeling nonlinear behavior of Diagrid members and selection and scaling of ground motions, nonlinear response history analysis result, and then ended with the conclusions. Complex shapes such as twisted, tapered, tilted, and freeforms are now new trend in design of tall buildings. Especially twisted and tapered are most popular in near project due to its wind consideration. A variety of structural systems such as outrigger, Diagrid, dual core system, and so on can be used to achieve this complex shape. Engineers are trying to find a regular structural solution, even though the architectural shape is non-regular. However, sometimes vertical member cannot remain vertical to achieve the desired architectural shape. Okay. And there are many issues for structural design of complex shaped tall buildings. Construction sequence analysis for gravity load will be the essential at preliminary design stage for the complex shaped tall buildings. And performance-based seismic design approach can be needed because following the current seismic design code for structural irregularity may give us uneconomical design result. Since current design code for structural component are mainly based on the regular buildings, which is composed with two-dimensional frames. So we need to consider additional forces and deformation in the members in the complex shaped structures. Main challenges for design of a complex shaped structure is wind load calculation at the preliminary design stage. Current wind design code does not tell us how to compute the wind load for the shape beyond the regular ones. Because previous experience and design skills are no longer valid, we need some system prototyping for complex shaped tall buildings. Actually, this work is done by Dr. Moon and Yale University and over there. And Professor Tamura in Japan conducted a series of wind tunnel tests to determine the wind forces and the wind pressures acting on tall building models with various configurations. They are doing more than 30 configurations. And twist shapes are good for the wind load because aerodynamic properties for crosswind response can be reduced. Wind optimized shape can reduce the member size, maintaining the loop displacement limit. However, the wind optimized structure can also be the earthquake optimized. This is the main concern of our research project. In tall buildings, seismic force such as story shear, and overturning moment are less than the wind forces. Thus, member design is usually governed by wind laws. But if the R factor is used in the calculation of the seismic forces, it means the R factor means the damage is allowed during the earthquake. If the seismic irregularity causes localized damage extensively in main structural member, it may trigger progressive collapse of an entire structure. And this is research objectives. First one is to identify mechanical characteristics of a Diagrid member and develop its analysis models for nonlinear response history analysis. And second is to investigate the seismic response of twisted Diagrid prototype models, which are redesigned using the current wind design code. Actually, at the beginning, I said this is the intermediate result, not the final one. So we are going to a next stage using the CFD analysis result to design the twist time model. And ultimate goal of our research project to be to provide a procedure and design tools for structural engineers to easily implement a performance-based seismic design methodology into practice. And this is a plan view of the Diagrid prototype model for our study, which is originally developed by the Professor Moon at Yale University. And it is a 60-story building with a height of 240 meters. And its plan size is 36 by 36 meters, and the core area is 18 by 18 meters. And the story height of the typical floor is 3.9 meters. And dead load for the design was 4.2 kilonewton per square meter, and live load was 2.5 kilonewton. And this is a twisted Diagrid prototype model. The model -0 is not twisted vertically. It's just straight model. And model -1 is twisted vertically at 1 degree per story. So the total twisting angle at the loop, because this building is a 6-story building, so total angle will be 60 degrees. And the model -2, it is twisted at 2 degrees per story, and the total angle will be the 120 degrees. And this example building was assumed to be located in the Seoul, in Korea. For this region, Beijing wind speed is 30 meters per second for 100-year return period, and exposure is B. And code-based wind design for each prototype model was conducted without considering wind load reduction effect due to the twisting, as I mentioned in the earlier slide. And for the seismic load, R factor of 4 was used for the system. And this R value was suggested by SOM in the technical note of CTBUH 2010. And because Seoul belongs to the seismic zone 1 in this table, 0.22G was used for the calculation of MCE, spectral response acceleration, at a period of 1 second. This table shows a summary of linear static analysis using equivalent lateral load. As the twisting angle becomes larger, the natural period here and wind forces here is increased. Thus, and for this region, the total weight, because the deflection is going to larger and force is larger, so we have to increase the size of the member. So total weight of steel is for this model 0 is 95, but here 2 degree twist model is 151,000 kilonewtons for the weight. And this is a comparison of wind and seismic force distribution along the levels. And the wind forces are generally larger than the seismic forces because we use R factor to calculate the seismic forces. And for the floors, over 50 floors upper, then the seismic forces are slightly larger than the wind forces because it's due to the effect of a higher mode. And this is a comparison of the size of Diagrid member for each prototype model. So as you can see, because the 2-degree twist model cases, the member size is larger than the straight and the 1-degree twist model. So as you can see here. And this plot shows a drift ratio and strength DCR. DCR means the demand capacity ratio distribution along the height for each model. And drift ratio for all model was actually drift ratio is here, and this is the strength DCR. And drift ratio for all model was less than 0.004. It's very small. And the strength DCR cases, from here you can see that in the lower level, because it's a 60 story and this is ground level, and it's mostly it's more than 0.5. In some cases, it's approached to the 1. That means it's almost approached its capacity. So basically, Diagrid member is a brace member. So it takes a lot of axial forces. Basically, the capacity is determined due to the buckling. And listen to guidelines for seismic design of tall buildings, TBI, and the Lone Climatic MKA talk about this issue in the Monday, and requires the 2 design levels, serviceability and the maximum considered earthquake, MCE. For serviceability levels, the response spectrum analysis can be used with the 43-year written MRI. MRI means a mean recurrence interval, and transient drift limit is set to 0.05, and elastic DCR limit is set to 1.5. And for MCE level, the nonlinear response history analysis should be conducted using 7 ground motion pairs with 2400 and 75-year MRI. Maximum transient drift for this MCE level is 0.045, and maximum drift is 0.015. There are 2 types of action for Oxytom's criteria from the nonlinear analysis: deformation control and force control action. So actually, this table comes from the ASC 41-06. And deformation control action allows ductile behavior after yielding or buckling. And also it provides acceptance criteria according to deformation level. Why? So deformation control means that you can consider the beam plastic hinging or elastic or inelastic buckling of a brace member. But why? Pulse control action does not allow ductile behavior. So basically, it's a brittle behavior, represents brittle behavior. So, or sudden loss of pulse. And ASC 41 stated that axial load in the brace member belongs to deformation control. However, actually, this is some typo, not the brace. It's a Diagrid member behavior produce considerable brittle result. Why? Because the Diagrid member takes a gravity load. Because in Diagrid system, there is no vertical column. So the brace, actually the shape is a brace, but it takes all the gravity load. So once the Diagrid member buckle, then there's no way to recover its deformation, original state. And seismic hazard spectrum was evaluated using the hazard factor. Korea does not have a lot of earthquake data enough to establish distinguish seismic hazard and Newton period relationship. So hazard factor, which was provided by Earthquake Engineering Society of Korea, was used in this research. It's showing in the bottom, the table. Serviceability check was conducted using 43-year latent period earthquake. All models were under drift limit. Strength check was omitted because the member design was determined mainly by the wind forces. There are many overstrengths in this serviceability stage. The member is mainly axial forces rather than bending or shear. It's usually classified form active structure, which is differentiated from the non-form active structure, such as a beam. However, we add a beam element to capture bending deformation, which occurs frequently in the lower axial forces. So that means when you check the bottom level, the Diagrid member takes a lot of axial forces, but in the top level, actually there's no little gravity load, so it takes some bending action, not the axial action. So we combine two elements in the, actually we use a Perform 3D computer software. So we combine the two elements. One is an inelastic bar element, and another, let me back to here, is inelastic beam element. This slide shows inelastic bar element properties. This model can reflect axial behavior, and in the compression, it can show the buckling strength calculated using the Euler equation. The modeling parameters and acceptance criteria for deformation were evaluated from using the ASC 41-06. And this is for the inelastic Pima beam, so it's very familiar from you. And beam time element was also added to the same member. But when it modeling this, it's only for the purpose of this adding is monitoring the flexural behavior. And we also conducted a PM interaction check for comparison of axial force and the moment history in Diagrid members at the lower levels. So this is the result from the push-up analysis. This shows that axial response is much larger compared to the bending response. So that means in the lower level, the behavior of a Diagrid member is governed by axial force, not the bending. And this is for ground motion selection. 3 pairs of ground motions, including 2 perpendicular directions, was selected. And they are scaled to the MC level spectrum, and scale factor was selected using minimum geo mean values. According to ASC 7, we use a maximum response as a demand. And this slide shows the result of a dynamic story shear distribution along the height. And largely twisted type results in the larger base shear. So here base shear is larger for the model 2. And also pulse type earthquake, because there we selected several earthquake data, and one is which is from the Loma Prieta is a pulse type earthquake. And this here is a green line. So in this case, this pulse type earthquake affected very largely to the base shear. And this is a transient drift ratio along the story level. Pulse type earthquake in this case also affect largely to drift ratio in upper level. And also from, you can see that from model 0, we can see a lot of cantilever action. I mean, a lot of flexure deformation is occurring in the upper level. And we are thinking this may be due to the higher modal impact. And this plot shows a residual drift ratio, and the residual drift ratio was checked at the story where the maximum drift happens. So it's from the loop story, the floor, and actually there is some difference between each model, but there is a little, almost nothing for the residual deformation from this analysis. This slide shows acceptance criteria, which is a demand capacity ratio check for both axial and bending action along with the story level. Blue dot here represents the bending, and red dot for axial behavior. So you can see that in the bottom level, the blue dot is larger, so that means axial force is governed, and in the top level, the bending is increased compared to the actual force. And this Shear of this block also estimated based on the immediate occupancy level, which is about the yielding point. And this result shows that actual action is governed at a lower level because of accumulated gravity load. And on the other hand, the bending action is dominated at the upper level due to higher modal impacts. I already talked about this. And as you might recognize, the significant deformation didn't happen here because basically when you do some nonlinear analysis for steel moment frame, then usually we can have a large deformation and plastic strain. But this is a form-active structure. Basically, it's a truss. So actually, deformation is not large, but the strength this year is very big. So it's only the immediate occupancy level, but it's almost about buckling. You're almost going to failure. And this is a conclusion for today's presentation. And code-based wind design may increase the member capacity in a largely twisted structure because of weakened stiffness and larger windward areas. And second is if the Diagrid members are classified to force control component, member in the low level could exceed the buckling strength. Diagrid members in upper story exceed the drift limit due to higher modal effect, and also in the case under the pulse type ground motion. And composition of inelastic bar element and the bending element provide quite a reasonable estimate. And thanks for your attention. Yeah.
Okay.